My name is Flash Isaac, and I'm a teacher from the future. When I was much younger, I saw thousands and thousands of people fail Jamb and unable to gain admission. This made me travel in time. Now I am back with the Flashlearners Jamb app and a series on YouTube tagged 120 Days to Jamb. My mission is to help you blast Jamb and as well get justice for everyone who Jamb has served breakfast. This is episode number 63 of the 120 Days to Jamb Chemistry with Flash Isaac. In this episode, we shall be looking at extraction of metals. Now, metals generally do not exist freely in nature. You cannot just see sodium and say this is sodium. Sodium, come. You can't say that. They don't exist on their own. You can't see sodium strolling or calcium doing big boy. No. Metals exist in combined form with other elements. You see them bundled. You therefore have to remove that particular metal you are interested in. The process of removing the metal or bringing out metal you want in its pure form is referred to as extraction of metals. Now, the combined form in which metal is found, or the impure form, or metal combined with other elements, before you remove that metal, that combination or that form that metal exists in is referred to as the ore of metal. Ore of metals. We therefore have to extract metals from their ore. There are three principles of extraction of metals. The first one is concentration of the ore. You need to concentrate the ore. Anytime you hear ore, take it to be metal combined with other elements. So we concentrate the ore, the combination. How do we concentrate ore? We can do that by washing. For example, in tin ore, when you wash the ore, you are concentrating the ore. Tin ore is cassiterite. Or you do that by froth flotation or by magnetic separation. Example, copper ore. Froth flotation is for zinc ore. The second principle of extraction of metal is roasting in air. You roast in air to extract the metals. And the third principle is extraction proper, which is what we are interested in, extraction of metals. The method we employ in extracting metal depends on how reactive the metal is. For very reactive metals like potassium, sodium, calcium, magnesium, and aluminium, popular scientists can make A. The first five, they are very reactive metals. For them, we use electrolytic reduction, electrolysis, to reduce them. For moderately reactive metals, after aluminium, you have Zu in tin low. So zinc, iron, tin, and lead, these are moderately reactive elements or moderately reactive metals. To extract them, the method we use is chemical reduction. Now, for the least reactive elements or least reactive metal, mercury, platinum, blah blah blah, we use thermal reduction. The very reactive metals, they normally exist as chloride, hydroxide, or oxide ore. Chloride or hydroxide ore or the oxide ore. For moderately reactive elements, they exist as triazocarbonate or as sulfide ore. For the least reactive element, they exist as sulfide ore. In summary, the principles of extracting metals are concentration of ore, roasting in air or oxidation, and the main extraction. And to extract metals, the method of extraction are electrolytic reduction, chemical reduction, and thermal reduction. The method you finally employ, whether to use chemical reduction, thermal reduction, and electrolytic reduction, is how reactive the metal is, or the metals are. For the very reactive metals, potassium, sodium, calcium, magnesium, and aluminium, we use electrolytic reduction. And these guys exist as chloride ore, hydroxide ore, and oxide ore. For the moderative reactive elements, we use chemical reduction. And moderative reactive metals exist generally as triazocarbonate ore and sulfide ore. Then, the least reactive metals exist as sulfide ore, and we extract them by thermal reduction. Now, let's see the top metals and the way to extract them using electrolytic reduction. Then, in the next episode, we shall look at all these metals and their ore. Let's see if the reactive metals actually exist, or the nature of their ore is chloride ore, hydroxide ore, oxide ore, and so on. We are going to find it interesting in the long run. We've been able to establish that the methods of extraction of metals depend on their position in the series, or depends on how reactive they are. And we are also able to establish that the very reactive metals, or the most reactive metals, are extracted by electrolysis. Jamb expects you to know how these metals, top 4 metals, are extracted via electrolysis and the things you should know. And Jamb also expects you to know the ores of certain metals, which we shall look at in the next episode. Sodium, calcium, magnesium, and aluminium. The electrolytic setup, or the electrolytic cell used in extraction of sodium, is referred to as down cell. And like I always say, everything I say in metals and non-metals are past questions, and they are set exactly like that. Reason I ask you to get the Flashlearners Jamb app to answer questions, because everything is like that. The electrolytic cell used in extraction of sodium is dash. It is the down cell. For calcium and magnesium, we don't care about the name. For aluminium, it is whole cell. The electrolytic cell for extraction of sodium is down cell. For aluminium, it is whole cell. All these are hot cake questions. Now, I told you that metals are not found in free state, they are found in combined state with other elements, and that is referred to as ore. I also say that for very reactive metals, their ores are usually the chloride ores, the oxide ores, and hydroxide ore. For sodium, the ore is sodium chloride, that is rock salt. Sodium is found in combined form with chloride. For calcium, it is found as calcium chloride. Magnesium exists as magnesium chloride. Aluminium exists as bauxite. In this case, it is an oxide. Bauxite is Al2O3.2H2O. This is bauxite. In electrolysis, like I told you, electrolytic cell, there is a direct current source, and we have the two electrodes. Anode being the positive electrode, cathode being the negative electrode. Then we have the electrolyte, the compound which decomposes to conduct electricity. And we have preferential discharge of ions. All these are the cathodes for the electrolysis, these are the anodes. You need not know all these, the cathode and the anode. They are not hot cake questions. But for knowledge, in down cell, the anode is graphite and the cathode is steel. In calcium, or extraction of calcium, the anode is graphite and the cathode is steel. For extraction of magnesium, the anode is carbon and the cathode is iron. For extraction of aluminium, the anode is graphite, the cathode is graphite. I think this one is simple and you should know it. For aluminium, the cathode and the anode are the same. For sodium, the cathode is graphite, the cathode is steel, and the anode is graphite. What are the things you should know in down cell or extraction of sodium? 1. Calcium chloride is added to make the process cheaper. So, what is the role of calcium chloride, or why do we add calcium chloride in the electrolysis or the extraction of sodium or in down cell? It is simply to make the process cheaper. How does it make the process cheaper? It reduces calcium chloride reduces the melting point of sodium chloride from 800 to 600 degrees. As the melting point reduces, which means we need less current for the ions to dissociate and migrate. In extraction of calcium, we use calcium fluoride to make the process cheaper. Why? To reduce the melting point. The same thing. In magnesium, we use sodium chloride or potassium chloride to reduce the melting point of magnesium chloride. In aluminium, the process is expensive, very, very expensive. Why? Because of the constant depletion of the anode. This graphite keeps getting used up, it keeps depleting. So the process is expensive. We don't have things to really add to make it cheap. Like for sodium, where we need to add calcium chloride, like calcium, where we need to add calcium fluoride, like magnesium, where we need to add sodium chloride. Something else you should know about the electrolysis of magnesium in whole cell is that this bauxite you are seeing is not pure. The first step is to purify this bauxite. How do we purify bauxite? We purify bauxite by adding sodium hydroxide. When you add sodium hydroxide to bauxite, it should be purified, and the pure form is Al2O3, which means .2H2 will be out of it. Al2O3 is referred to as alumina. So after purifying the bauxite to get alumina, you dissolve this aluminium in cryolite. So this cryolite acts as solvent for the aluminium. As the alumina dissolves, it begins to conduct electricity, because electrolytes conduct only in their molten state or in solution. Cryolite is Na3AlF6, that is sodium hexacyanoaluminate forever. Ladies and gentlemen, that is it for this class. I hope you found this helpful. Get the Flashlearners Jamb app, begin to play with questions. Subscribe to this channel so you'll be notified anytime I publish new video. You'll get the notification once your notification bell is turned on. What else? Play with questions, enjoy life. If you have anything to discuss or anything to tell me, reach me via my social handles. Get the app at flashlearners.com or search Flashlearners Jamb on Play Store or use the direct YouTube description. Make sure the app you install is Flashlearners. It is going to help you pass very, very well. See ya in the next